Okay, so we have a triangle with in-center I and A, X-center J. Another in-center and X-center problem. Wish there was a way to draw X-centers with GeoGebra. So the A X center is J. So let me shrink this. Yeah, the only thing with X, I like X center problems a lot, but they take up a lot of space. So use our in-center X-center lemma again. So this is J. A prime is the diameter. Okay, so we're going to want to let O be the center of that circle. So O is the center of C. Oops. And why didn't that work? Oh, whoops, that's the wrong circle. We want the center of D. Okay, so O is the center of D, and then we didn't want to do that. Sorry, I will get it right this time. O equals center of D. There we go. Reflect A across it, so we get A prime. And H1 and H2 are the orthocenters of BIA prime and CJA prime. So H1, that's BI A prime 4, and H2 CJ A prime 4. And we want to show H1, H2 is parallel to BC. All right. Let me draw a couple things. So basically, okay, so BI A prime So basically, another way to say it is B is the orthocenter of I H2A prime. Yeah, let me try to get a nice figure. So okay, so we want CJA prime. Wait, EIA prime and C. Yeah, I think I don't need some of these points. Let me delete this. Delete this. Sorry, I'm going to read the chat just a second. So we have BIA prime. And H1 is the orthocenter of that. And then we have CJA prime. So Yeah, I wonder if they kind of look similar, those two triangles, right? But yeah, so sometimes the H1 lies inside BIA prime, but H2 lies outside CJA prime. I don't know if it's always going to be like that. Or can we make both orthocenters? I don't think we can make both orthocenters lie in the side of the triangle. I think one's going to lie inside one of them and the other is going to lie like outside of the other, right? That's what it looks like. So IH1 is parallel to AB. Interesting. So wait, IH1 is parallel to AB.
You intersect IH1 with AH2.
Yeah. IH1 and AH2. Hold on one second. So
IH1 with JH2.
all right. Shrink it a little bit and yeah. Let me just like that. Is it okay if I
It's not
intersect
the
it?
intersection point. IH1 with JH2.
Oh, JH2. I'm sorry. I thought you said AH2. So yeah, I can delete this. Is it obvious that those triangles are similar? I don't even know that. So BIA prime and CJH2. One second, guys. All right. So IH1 is parallel to AB. Sorry, guys, 1 second. All right. Hopefully I won't have to get up anymore. Sorry, guys. Okay.
One way to prove is BH1, CH2, and AE are concurrent. Maybe we can prove that.
EH1, CH2, and say it one more time.
BH1, CH2, AE.
AE?
Yeah, if we prove that, we are done. But I don't know whether it is easy or not.
Okay. Maybe the SARGs would help with that.
After
Yeah,
that,
the
we will use
short, sorry. Oh no. If we have that, the short solve the problem.
That would solve the problem, is what you're saying.
we cannot use DSR because we will use it to prove that H1, H2 is parallel to BC.
Okay. So you kind of use the SARGs in the reverse direction, I think, right? To get there.
Yeah.
So we could prove that CH2 cut AE at a point T and BH1 cut AE at T prime, and we can prove T prime A over T prime E is equal to T A over T E.
Okay.
Use
Hold
the
on.
ratio.
Hold on one sec. Let me write that. So we call this T prime, for example.
Yeah, okay. And maybe we might calculate the ratio T prime A over T prime E.
Okay.
Yeah, and if we could prove the same with pH1, so we are done. That is maybe we could use let's say
I forgot, how did we define point E?
that is IH1 cut JH2.
Oh, okay. Got it.
You can define it as it will be easier from I parallel to AB and the line from I parallel to AB and the line from J parallel to AC concurrent E.
Okay. J parallel to AC. So it's
we
like a
can
parallelogram. Yeah.
We can define BH1 as perpendicular from B to IA prime. So we won't use that H1 is orthocenter, just we will use one perpendicularity.
That makes sense. Because yeah, IE is perpendicular to A prime B. So yeah, we drop that perpendicular, let it intersect at E. And then we drop it. Well, but I mean, it's kind of similar. I mean, it's kind of the same definition because E is defined as like, well, I guess it's parallel to AB, but we know AB is perpendicular to B, A prime, so. Makes sense though. Okay, so Feng's idea was maybe we could show AT prime over T prime E is equal to AT double prime over T double prime E. So yeah, we know JE is parallel to AC. So yeah, I think that's what Feng was trying to do. Or Dat Feng. Yeah, so how can we find AT prime over T prime E? So that's the same as AC over H2E. Interesting. So basically, we could let C, well, so we want to show that H2E over H1E is AB over AC. So really, we want to show H1E, H2 is similar to BAC, right? I mean, that would be, yeah, that would be the same thing. Yeah, and now I'm just going in circles, yeah. Oh yeah, we have to use something about the fact that it's the in center and the X center. Let's check chat. Maybe we can use I A prime equals J A prime. Oh yeah, because angle, this is the right angle. That's a good point. So were there like two triangles that I thought were similar? Wait, is BIA prime? I was going to ask if BIA prime is similar to ABC, but that can't be true. Uh, okay, so BIA prime and CJA prime. A prime, D, and E. It looks close. Let's see if that's true. Ah, interesting. Yeah, it looks like they're collinear. I did not realize that. So I'm just going to make it a segment. Is that obvious? So basically, we're saying the perpendicular from I to B. I'm going to delete T prime for just a second. If you guys want me to add it back, let me know. But yeah, I'm not sure about using Desargues' theorem here. So, do you have a proof that A, D prime, and E are collinear, or is it something you observed?
We just use angle chase, Michael.
Angle
So-
chase.
Yeah.
Okay.
That is because so angle EID.
Mm-hmm.
So we have I is perpendicular to A prime B,
Okay.
and JE is perpendicular to A prime C, right?
Yes.
So we just need proof that angle that makes from A prime B and AD with A prime C and AD is equal, and you let A prime C cut AD, so the two angle is equal to each other.
Okay. So like, did you say if you let A prime C cut AD?
Yeah. So B A prime D will equal to F A prime D.
Mm-hmm.
Yeah. So and EID is equal to B A prime E.
EID is B A prime D.
Yeah, and so with EJD is equal to D A prime F.
Okay. I think I see what you're saying. And that would prove that. That would prove that these three are collinear, right?
Yeah.
Okay. All right. I might add point F back in when I do the final solution. Oops. It looks like this circle passes through O. I'm going to move it a little bit so it doesn't look like that. Like that. Sorry. Hmm. Let's see. Now I'm kind of liking the SARs again, but yeah. Yeah, maybe it's worth drawing like JA prime. The CH2 is perpendicular to JA prime. Now I'm trying to use orthologic triangles again. So if we have triangle IA prime J and BC, let's see. So IA prime J and BCD. Let's see. Two E. Let me try something. So I'm going to take this point and I'm going to drop a perpendicular to AD. I wonder if F is the midpoint of IB. I don't think so, but it almost looks like it in this picture, but I don't think it is once I move stuff. No, yeah. So, but if I drop a perpendicular, actually, yeah, I'm just getting a little confused here. Let me redo that for a second. So for any point on this line, we want to show that I, A prime J, and that point with B and C are orthologic. J is the X center of ABC. So it's the reflection of I over point D. Is there any special point on this line? So we know the perpendicular from I to BC is G. And then I'm going to delete this. Just a second. Yeah, I'm not sure where to go from here. You spend a couple more minutes and then move on to the next one. I wonder if there's like a way to flip the problem around. So like let H2 be the point so that like, or like what if we draw the parallel through H1 and let it meet EJ at like H2 prime? And then we show that like H2 prime is the orthocenter of CJA prime. I kind of like that because that would give us a couple things to work with, right? Then we would know that this triangle is similar to ABC. Then we could use the Sarg's theorem. It almost seems like an easier way Or we could try using the other definition of the orthocenter. So like, if you reflect it over the side, over any of the sides that lies on the circumcircle. Let me draw like what if I drew the circumcircles of IA prime B or CJ prime A? So if we reflect H1 over each of these sides, it's going to lie on the circle. And the same is true with this circle. You guys want to move on to the next problem and come back to this? I'll give it 5 more minutes. Okay. I will do that just to keep it going. Okay, so we have a triangle ABC, and we draw the incircle and circumcircle. Okay. And it's tangent at E and F. So E and F. Then let EF and so I feel like I've seen a few problems like this, where you let like EF intersect the circle at 2 points. And often they use like poles and polars a lot because P and Q are both on the polar of A. So let's see if that helps at all. M is the midpoint of BC. R is on the circumcircle of MPQ. And they're calling that gamma. So that MR is perpendicular to EF. And we want to show AR and those 2 circles concur. That's interesting. So this is point R up there. And we want to show that AR passes through this point right here. So basically AR and G are collinear. So I'm gonna hide
PQ and BC.
Oh, you want to draw the intersection of PQ and BC?
Yeah.
Yeah, that's often helpful. Let's see, maybe I can make it a little closer to, there we go. Whoops, this is just bugging me. It doesn't say Taiwan. There we go. And
we can prove that in circle and the circle of PQR and BC are concurrent.
Okay, hold on just a second. Is there one more thing I have to draw? Oh yeah, MR. So by the radical axis theorem, or that these concur basically is what you're saying.
Yeah.
These three.
Power of point.
All right. Because DE times DF is DP times DQ, which is DB times DC, which is DH squared. Yeah. So yeah, we have to.
DH times DM equals to DB times DC, it equals to DP times DQ.
Yeah, because since M is the midpoint of BC, and
The harmonic bundle.
yeah, harmonic bundle, yeah. So yeah, it's just showing A, R, and G are collinear. And almost like, I don't think AR is perpendicular to BC, is it? That would seem really strange. Yeah, it doesn't look like it here. Yeah. Okay, so yeah, we have this concurrency right here. So yeah, we have the perpendicular to EF. I wonder if it's worth dropping the perpendicular from H to EF, because that would be the Sharkey devil point, and maybe it lies on that line. I don't think it lies on that line. Or B, G, and Q collinear. No, there's no way. Sorry. Because if B, G, and Q were collinear, then P, G, and C would have to be collinear by the same argument. Now, let me call this, instead of I, let me call it like L. So I wonder if HL is, so I wonder if HL and I are collinear. I think so. So let me instead do it this way. So I could, we'll draw both these points. So I think R, A, K, and G are collinear. I can't prove it, but whoops, sorry. Interesting. Yeah.
Introduce the Sharkey level point.
The Sharkey, so J is, oh, you mean let AJ meet the circle? Or no,
IJ.
drop. I think you mean this point, right? This
Yeah,
point.
also IJ passes through this point.
Yeah. All right. Um, and then if we let AJ meet the circle, I wonder if no, I'm sorry. I don't know if there's too much we can do at that point. But yeah, so we want to show this line. Can we first show that like AK and G are collinear, and then yeah, I guess the first step is to show AK and G are collinear, and then maybe we could show RK and G are collinear. Hmm.
So we need to prove that EF, KG are harmonic quadrilateral, right?
BF,
EF, K, and G.
EFKG is harmonic. And yeah, I've seen that before. I think that was on IMO 2019 number 6. Let's see. So basically, yeah, IMO 2019 number 6, I think they show, oh no, I think it was actually, okay, no, but sorry. So we want to show EKFG is harmonic, right?
So if G, K, EF are harmonic, so G is the Michael point of the. Let's call H prime is the orthocenter of the triangle HEF. So G will lie on the circle.
Okay, so so you want to draw the orthocenter of HEF?
Oh no. Hold up.
Okay. Yeah, take your time. Can I draw LH? Yes. So LH and AI, I think, are concurrent on the circle, right? If I remember. Yes.
In that EKFH, EZFK is harmonic quadrilateral is very easy. You can draw,
EHF.
you can draw GH and AL, like GH and AL.
So AL.
Yes, GH will concurrent at equi. Yes.
Okay, so if we can, I'm sorry. Oh, by the radical axis theorem, these concur, right?
Yeah, yes.
Okay. And then
and we have a common ratio that OJEF is harmonic.
Okay.
OJEF is harmonic by because let's call the midpoint of EF.
Okay.
Because JS time JS sorry, can I type JS JO equal to JK JE JF. So it implying that OJES is harmonic and so that hat OJEF hat OJEF is harmonic. So EGKF is harmonic quadrilateral.
Because you project through H onto the circle. That makes sense.
Yes.
I like it. Nice. It's a good way to do it. Okay, so yeah, so we know that that's harmonic. So we know A, K, and G are collinear. And then we just have to show RLIs on that. And I think you mean JS times the JO is JL times JI, is JE times JF. Yeah. And so since S is the midpoint of the F, then it shows they're harmonic. I like that. And so A, K, and G are collinear. And then by Sharkey double stuff, we know that L, H, and N are collinear. And MR is parallel to AN. So to show that K, A, and R are collinear, can we use the parallelism somehow? Because we have a lot of parallel lines. So IH is also parallel to MN. I don't know if that helps. I wonder if PMQR is harmonic. Well, that's hard to tell here. Yeah, I would have to change the diagram a lot. I don't think so. No, it's not. But yeah, with so many parallel lines, it feels like there has to be a way to show this. So we have the perpendicular from M to EF, I to EF, and N and H to EF. How do we show? I mean, it might be easier, let GA meet the circle at R prime, and then we want to show, that might be easier. So call it R prime. We want to show R prime M is parallel to both AN and KH. Oh, so we proved that using harmonic quadrilaterals. So EKFG is harmonic. So Hoy just proved that. Nguyen Hoy. And once you know that, that means the tangents at E and F to this circle and GK are concurrent at A. Okay, so we want to show RM, whoops, is perpendicular to PQ. Or parallel to AI. there anything else we can say about R? Is A, L, G, and H cyclic? Let's see. Yeah. And that's probably by power of a point, right? Because OL times OA is, let's see, ALGH is OE times OF, which is OG times OH, right? So yeah, those are cyclic. So yeah, I mean, really, we can hide a lot of information in this problem. We can let the perpendicular from H to EF meet the incirclet K, and we can let KA meet. Oh, but we do need P and Q. Yeah. So we need that circle.
Well, the rest is angle chasing.
Oh, really?
GRM equals to GHB, and it equals to GKH, and it equals to GAI.
Okay, so you showed GR prime M is equal to GAI.
Yeah.
Interesting. Okay, so I'm going to start. So GR prime M is G. Why doesn't this show R prime? R prime. GR prime M is GHB, which you're saying is GAI.
GKH, and it is GAI.
GKH.
Because it's tangent in circle.
Interesting. Okay, so I'm going to start writing it up. Okay, so we have so first of all, we have B, H, M, and C are in harmonic conjugation. Or sorry, B, C, H, D are in harmonic conjugation. So that means that dB times dC, or dH times dM is dB times dC is dP times dQ. So and so that means PQHM is cyclic. And then once we know that, let the perpendicular from H, the perpendicular from H to EF intersect the circle at K. And then first we're going to show that AK prime or AK and G are collinear. So by the radical axis theorem, GH, AL, and EF occur at a point O. then, sorry, AL. And then we have O. We have so I'm going to write out what sorry, what Nguyen said. So we have JS times JO is JK is JL times JI. Sorry, I'll write it here. So S is the midpoint of EF, and so O J S F. I'm sorry, O J E and F are harmonic. So and then projecting through H onto omega. Then we have HEKF is harmonic. By the way, I should say in the very beginning, let PQ intersect BC at D. So, and then, so that means that GK passes through A. Okay, and then let GA meet. Did we need that GK and A are collinear? I think we did, right? Yeah. Let GA meet meet the circle HPQM at R prime. Then we have angle we wanted to show that angle GKH is angle GR prime M. So GR prime M is GHB. Which is equal to GKH. There we go, that's where we use it. Which is, so that means that KH is parallel to R prime M. And that implies that R prime equals R. That implies AR omega and gamma. All right. Now that's a really nice solution. I like we used a lot of harmonic stuff. So yeah. Harmonic quadrilaterals, and then we used this identity about harmonics twice. All right. I think I can get rid of this right here. All right, thanks everyone. So I will move on to the next problem. We have about 40 minutes left here. So we have Taiwan always has these very short problems. which is kind of interesting. We have a triangle with orthocenter H. And then on its circumcircle, we choose an arbitrary point P. I'm guessing that should say circumcircle, not circumcenter. So P, let M be the midpoint of HP. I feel like I did a problem like this from like where I have like a midpoint of HP where, whoops, where P is arbitrary. I think Evan Chen's channel had a problem like this that I did. So it looks like homotheties might be a good idea because the reflection of H over each of the sides lies on the circumcircle. So basically M lies on the 9-point circle. So M is any point on the 9-point circle. Now we find 3 points D, E, and F. So AP is parallel to HD. BP, so we draw AP, BP, and CP. Interesting. And then we draw the parallels to them through H. That's interesting. AP, BP, and CP. So the parallel to AP, we want to see where it intersects BC. And then CA and AB. So BC, then the parallel to BP, E, and F, and we want to show that D, E, F, and M are collinear. Interesting.
Can you draw the Simpson line?
The Simpson line of P. Yeah, hold on just a second. Let me hide some stuff. Hide. Oops. Did I do that? So that's parallel, and that's parallel. And then we want the Simpson line. So draw the perpendiculars. P to AB. Or, yeah, let me do this one instead. So does the Simpson line pass through M?
Yep.
Oh yeah, because it's well known that the midpoint, yeah. Okay. Yeah, no, now I remember that's a well-known fact. So we could draw the other perpendicular too. I'll do that just to make it look nicer. So there we have the Simpson line. Let me check the chat. The Simpson line. So if you drop the perpendiculars from P to all three of the sides of ABC, they all are collinear. So P to AC is J, P to AB is I, P to BC, the perpendicular is G, and they're collinear. And it's not a very hard proof. It's just an angle chase. So if you haven't seen it, I'd recommend trying to prove it. Okay. So yeah, it's well known that the Simpson line passes through M. And
is there a relation between them? And draw EFT too.
yeah. So that line.
Yeah. Okay, it seems irrelevant. You can delete the Simpson line.
Okay. But yeah, if we find out later that it's useful, I could add it back in. Oops. Let's check the chat. So that's I forget the whole proof. Yeah, I actually don't remember the proof, but I proved it before. I proved it like a year ago or something. Something to do with homotheties, I'm sure. So M lies on the 9-point circle. Maybe I should draw that 9-point circle.
Can you draw the line SP tangent to circle of ABC?
The tangent line.
Yeah, maybe they are parallel.
So that
are they parallel?
yeah. Oh, they might be. They look parallel. I guess. Oh, you know what? No, not necessarily. It just looked like it with that triangle, I guess. But in general, they're not parallel. So actually, you know what? I could, I think GeoGebra has this dilate. So if I take this, the circumcircle of ABC, why won't it let me do that? Dilate. Select, oh, first you have to select the object, then the center point, and then the factor. There we go, we get our 9-point circle. Isn't that nice? So M lies on it. And so as we move P around, M stays on it.
Is it tangent?
Tangent. Oh yeah, it does look tangent to the 9-point circle. Yeah. Let me try moving A around, but I think, yeah, in general, it looks tangent. So what we want to do is we want to draw the tangent to the 9-point circle at M.
Actually, I'm not that sure. Can you select
Different points?
Yeah, me too.
So actually, yeah, it might intersect again. Yeah. Yeah, no, it's not tangent. I got too excited there. Yeah, let me draw a bigger picture. So yeah, because if you do it like that, now it's clearly not tangent. Yeah.
We can check what Anmol said.
Let's see what Amal said. If I is the midpoint of BC, then IM is perpendicular to AP. Interesting. So I'll call this I. Or are you okay if I call it OL? Yeah, I was gonna say. Do you see a proof of that, or that's something that you observed just by playing around? It's a lemma. Interesting. LM is perpendicular to AP. So if we let O be the center of ABC.
I remember it was something about its proof was something about the homotopy in H.
Okay.
And Euler circle.
Okay. So basically, that's the same as saying, so the proof used homotopy and Euler circle. So let's see, if I let it, I'm just gonna use the reflect. So if I let A prime be A prime's the diameter, then we're saying P, oh, but L, M, and H aren't collinear. So, okay. Let me think. LM is perpendicular to AP. So I guess if we do a homotopy, if we take LM and we like scale it up by 2, so like I could draw HL. Oh, because HL meets the circle at the antipode of A, right? That's a well-known fact. So basically, yeah, because LM is parallel to GP, and it's well known that G is the antipode of A. So yeah, that makes sense. Interesting. Okay, so
What? I didn't get it.
yeah, so L is the midpoint of BC, and it's basically a well-known fact.
Oh, I now see it.
Yeah. So yeah, so LM is parallel to PG, and so that's why LM is perpendicular to AP. I solved something on this session. Yay. So, but Anmol was the one that saw it in the first place. Yeah. Let's see. So, are PF and G collinear? Let's see. MOLD are cyclic with diameter OD. So that's interesting. So angle OMD is 90 degrees. Because obviously angle OLD is 90, but OMD now so OMD is a right angle. GeoGebra moment. Why is that? Why is angle OMD 90? It's interesting. So what if we
Can you denote the midpoint of AP?
AP?
Yes.
All right. Let's call it something better. I don't know, R. Are GH and R collinear? No. But OR is parallel to GR, OR is perpendicular to AP, and LM is perpendicular to AP.
Can we show ORML is a parallelogram?
ORMF.
L.
I'm sorry, ORMF.
ORML.
Oh, ORML.
Yes, yes. It is a parallelogram because RM is a half of AH, and that is OL.
Oh, yeah. I saw that now.
Ah, nice. Okay, so RMLO is a parallelogram, and then where do we go from there? So once we know RMLO is a parallelogram, do you see how that solves it?
Wait a minute.
Okay, take your time. ABPH. I don't think APBH is a parallelogram. If you draw the reflection of H across BC as H prime, then OMR and ODH prime are similar. That's interesting. And yeah, we know the reflection of H over BC lies on the circle. I want to show, because I need to do reflect over line, not reflect over point. Oh yeah, if they gave GeoGebra an IMO, that would be so fun. Yeah. Yeah, I'm kind of glad I'm done with competitions, because yeah, now I can just do GeoGebra. A lot of parallel lines here. Complex patch does work. Yeah. I believe you. Yeah, it sounded like Melek was close. So yeah, maybe has an idea. Clear by GeoGebra theorem. Yep. BP and DH. I can label that if you want.
Actually, I've solved it, but now I couldn't figure it out again.
You forgot how
Yes.
yeah, I've done that a bunch of times. Let's see if we can figure this out. So let's see. So we know RMLO is a parallelogram. E, M, and I are collinear. I don't think so. So yeah, we only really need to show 3 of them are collinear. Well, maybe like, because if you do a homotopy about H, maybe you could like reflect H over points E and F, and then try to show those are collinear. Let's think. what could you do with the midpoint of AP? So we know OR is perpendicular to AP. Let's see. What if we do this and this? So let's think. What do we do with parallelograms? So RM. So we know RO is parallel to LM.
Can you draw the line LM?
Yeah. Kind of looks a little, thinking like a trilinear pole or something. So OM is perpendicular to MD by the outer butterfly theorem. Interesting.
Can you intersect DM with AP?
DP, or say that one more time.
DM and AP.
EM and AP. Yeah. Okay. All right. So
Actually, I'm not sure, but from outer butterfly theorem, can we prove that MD equals to
MD is equal to something?
maybe we can prove that OM is perpendicular to DJ from outer butterfly theorem, but I'm not that sure.
Oh. I think you might be right. And then if we did that, would that solve it?
Yeah, because DM is perpendicular to OM, FM is perpendicular to OM, EM is perpendicular to OM, so DEF are collinear. DEF, M are collinear.
Oh, because they're all perpendicular to OM. Interesting. Let me think about this for just a second. I'll read what Anmol has, because I think, yeah, Anmol looks like he solved it. So I forgot even what the outer butterfly. So I think the outer butterfly theorem says you have like you have a cyclic quad.
Yeah, actually, outer butterfly theorem proves it.
Okay. So as far as I remember, like the outer butterfly theorem, it's like you have a cyclic quad, and then you like draw the intersection. So like, do you see how to apply that? So like, how do you apply the outer butterfly theorem?
Normally, outer butterfly theorem says OM is, when OM is perpendicular to DJ, M is the midpoint. But we use the reverse of it.
Okay,
So there is a
so
line passing through M, and we intersect it with AP and BC.
oh,
This
but
is how
I
we do it.
think this is the normal butterfly theorem, just where the intersection points are off the circle, like
Actually,
so
I
yeah.
was watching your video. It's the same, I guess.
So like there's, I made one video on the butterfly theorem and another video on the outer butterfly theorem, right? So like there are two different theorems, right?
Yeah, this is outer butterfly theorem.
Really?
Because there's a line passing through M, and A
There's
and
all,
BC intersected.
okay.
We also have MD equals to MJ, so OM is perpendicular to DJ.
Okay. So I'm going to draw both. I'm going to write up both your solution and Animal's solution really quickly. But so let EF meet BC and AP at D and J. At D and J, and then so we have DM is equal to MJ, and that's because, is that because DPJH is a parallelogram? So basically, oh, butterfly does not work. Okay. All right, so I'm going to write up what Anmol wrote. Just for the viewers on YouTube. Thanks for writing it all up, Anmol. That makes my life easy. So I could just go like this. Okay, let the second intersection of AH with the circumcircle. Let Q and R, I just like capitals, be the midpoint of HW and PW. Then, whoops. Just gonna do this as fast as I can. I'll just leave it in lowercase for now. So I like how you wrote it up. Let's see. Let's see how this comes out. It's not bad. I thought it might be really messy, but it really wasn't that bad. Okay, so omega, I'm just going to delete J for now. Let's see. So omega is the intersection of AH with the circle. Or W, yeah. And Q and R are the midpoints of H, W, and PW. But so I'm going to delete R for now. But if we, yeah, if you ever remember your idea, yeah, post it on YouTube. So midpoint of HW and the midpoint of PW. So the midpoint of HW is just the foot of altitude. So this is Q. And this is R. That's the only reason I deleted point R, is because I wanted this to be point R. So then Q, let's see. Oh, where'd W go? Wait, no, this should have been W. Q is the midpoint. This should be Q. So this is Q. This should be W. And then we have QW is parallel and equal to MR. Okay. And OWR is similar to HDQ. Is that so? R is the midpoint of PW. Okay, so ORW is similar to HDQ. I think that would be similar to WDQ. So OW over WD, R over RM. Interesting. So OM is perpendicular to MD. I think this makes sense. I'm going to stop right here just because we're out of time. But so you're saying the angles between OW and WD is the angle between OR and WQ. OR and RM. So, okay, OW over WD is OR over RM. So yeah, you're saying there's a spiral similarity between ORW and OMD. It's basically a spiral, yeah. So basically spiral similarity between ORW and OMD. All right, well, I'm going to stop here because we're out of time, but this was a lot of fun, and for everyone who participated, thanks. So for those of you watching on YouTube, if you'd like to join a future session, feel free to email me at mgreenb801@gmail.com. The sessions are on Sundays at 8 a.m. US Central Time. Have a good one.